All right, so this is part 2 of section 3.4, and we're going to practice more with choosing our x to be the number of changes. Okay, so example 3 says an orange grower finds that if he plants 80 orange trees per acre, that the tree will yield 60 bushels of oranges. He estimates that for each additional tree that he plants per acre, the yield of each tree will decrease by 2 bushels. He wants to figure out how many trees he should plant per acre to maximize the harvest. All right, so we're going to make our x be the number of added trees per acre. All right, and we know that he's going to start, so his trees per acre, he's starting with 80, and he's going to add so many more. But he also knows the yield per acre starts at 60 and will decrease 2 bushels per added tree. Okay? So think about this. The yield that we have, so that yield that we're trying to come up with, is going to be the yield per tree times the tree per acre. Okay? So the yield per tree, so sorry, I wrote that down. Yield per tree. So that's 60 minus 2x times the trees per acre. If we multiply all of that out, our yield becomes 4,800 minus 100x minus 2x squared. Go back to your problem. We want to maximize the harvest or maximize the yield. All right, that's our key phrase. Maximize whatever. Take the derivative and find the critical numbers. Okay, so I want you to pause the video, take a few minutes and find that derivative. All right, so if you take the derivative, set it equal to 0, you end up with x equal to negative 25. Taking the second derivative shows you that y double prime is equal to negative 4, which is negative. So we've shown that we do have a maximized value at x equal to negative 25. What this shows is that actually if he will plant the 80 plus the negative 25 gives us 55. So if he'll plant 55 trees per acre, he will actually maximize his harvest. So he has too many trees right now. All right. And the graph is on the bottom of slide 11. All right, let's look at example 4. That'll work. All right, so a moving company wishes to design an open-top box with a square base whose volume is exactly 32 cubic feet. We need to find the dimensions of the box requiring the least amount of materials. All right, so if it's a square base, we know that all the sides are the same. So we can say that x is equal to the length of side of a base, and we can call y the height. All right, so we know the volume So what we want to find is the volume that, or we have this volume, we need to minimize those cubic feet. Okay? So if you look at slide 13, the volume, which we know is the length times the width times the height, which would end up giving us x times y, or x squared y, has to be equal to 32 cubic feet because that's the dimensions that were given. All right, you've got a picture of the box here showing you we've got the open top and the bottom and the sides. If we want to minimize the amount of materials used, that means we're minimizing the surface area. Okay, and the area would be A equals x squared plus 4xy, which x squared gives us the area of the bottom, and then x times y is the area of each side. So we have the area of 4 sides with 4xy, and that's what we want to minimize. Again, we've got 2 variables, so we've got to take somehow we've got to get rid of one of them. So what I'm going to do is I'm going to take this volume equation that we have, the x squared y equal to 32, and I'm going to solve for y. So I'm going to divide both sides by y squared, or by x squared, sorry, giving us y equals 32 over x. So now I can take my area function that I want to minimize because I want the least amount of materials, and that's going to give me x squared plus 4x times 32 over x squared. Oh, I forgot my squared over here. All right, if we simplify this, we end up with x squared plus 128 over x, which remember we can pull that x up to make it easier to differentiate. Under x squared plus 128 times x to the negative 1. This is what we want to minimize. So we want to take the derivative. A prime would end up giving us 2x minus 128 x to the negative 2. If we set this equal to 0, we can multiply by x squared on both sides, or not, yeah, both sides, and that would give us 2x cubed minus 128 equal to 0. Let me show you that step again, sorry. Oh, let me erase that much. So I have 2x minus 128 x to the negative 2. This x to the negative 2, remember, it goes to the bottom. This is where I'm getting to multiply by x squared on both sides. Giving us 2x cubed minus 128 equal to 0. We can add 128, so it gives us 2x cubed equal to 128. Divide by 2, x cubed would then equal to 64. And the cubed root of 64 is 4. There's our critical number, and we need to prove that it is what we need it to be. So if I take the second derivative, end up with 2 minus 256 x to the negative 3. If you plug in 4, take a second, plug in 4 and see if it is positive or negative. Okay, sorry, I realized I had a typo. It should be, a double prime should be 2 plus 256 x to the negative 3. When you plug in 4, you get that a double prime is 6, which is greater than 0, which tells us x equal to 4 is the minimum. Okay? Now, we were asked for the dimensions. So now we need to go back and find the dimensions of the box. We know that x is equal to 4. Okay, so when we plug that back in, let's scoot up just a little bit. So with x equal to 4, we know that 4 squared times y has to equal 32. And y would be 2. So for this problem to work, to have the least amount of materials used, we need to have the base be a 4x4 box square and the sides to be 2 feet tall. All right, and you got a picture of that on the bottom of slide 16. All right, let's keep going with the next one. Hi, dog. All right, so how would the preceding problem have changed if the material for the bottom of the box had been more costly than the material for the sides? So, for example, if the material for the sides cost $2 per square foot, and the material for the base, needing greater strength, cost $4 per square foot. Okay? Then instead of simply minimizing the surface area, we would also have to minimize the total cost. And here's the equation that they come up with. So cost equals area of bottom times the cost of the bottom per square foot plus area of the sides times the cost of the sides per square foot. Well, since the area of the sides would be just as before, this cost would be x squared times 4 plus 4xy times 2, or giving us 4x squared plus 8xy. From here on, you would proceed just as before, eliminating the y using our volume function and then setting the derivative equal to 0. It would be the exact same process and the exact same steps. Okay? All right, I'm going to finish this section on the next video.